Have you ever stopped to think about what really holds our world together? I mean, at the most fundamental level. It all comes down to molecules. But they're not just these random clumps of atoms. Nope. They have very specific three-dimensional shapes, almost like they were designed by an invisible architect who follows one single simple rule. So, let's dive in and uncover this secret blueprint.
You know, back in chemistry class, we all learned to draw molecules on paper, right? Flat, static, kind of boring. Like this one for ammonia. But here's the thing. That's not the whole truth. It's like looking at a flat blueprint for a skyscraper. It's useful, but it's not the building. The real world is 3D, and so are molecules. So the question is, what do they really look like out there in space?
And this isn't just some minor detail for scientists to argue about. No way. A molecule's 3D shape is, well, it's everything. It dictates what that molecule can do, how it behaves, and how it connects with every other molecule around it. Their shape is literally the secret to their power.
All right, so let's officially leave those flat, 2D drawings behind. It's time to step into the third dimension and start speaking the language of real molecular shapes. Okay, to talk about 3D shapes, we really only need two key terms. First, there's bond distance. Super simple, it's just how far apart two atoms are. But the real star of the show today is the bond angle. This is the angle between atoms, and it's the one thing that truly carves out a molecule's final shape. So what force is deciding these angles? Who is this invisible architect? Well, it turns out to be an idea that's so simple, it's actually beautiful. It's all based on one thing, the electron repulsion rule.
Now, the official, fancy name is valence shell electron pair repulsion theory. Yeah, it's a mouthful, which is why everyone just calls it VSEPR theory. And look, don't let the name intimidate you. The idea is incredibly simple. You've got pairs of electrons in the outer shell of an atom. They're all negatively charged. And what do similar charges do? They push each other away. They just want their personal space.
As the source material puts it, they just adopt an arrangement that minimizes repulsions by maximizing the distance between them. The absolute best way to picture this, imagine you have a bunch of balloons and you tie them all together at the knots. What happens? They don't just sit in a clump. They naturally push away from each other and spread out into a very specific, predictable shape. That is exactly what electrons are doing.
And what's so incredible is that this one simple rule, electrons pushing each other away, is responsible for creating just a handful of fundamental geometric blueprints that you see over and over and over again in chemistry.
Depending on how many of these electron groups you have around a central atom, anywhere from 2 to 6, they will just snap into one of 5 basic shapes. These are the big ones: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Think of these as the basic Lego bricks for building almost any molecule.
Okay, but hang on. Here's where we hit our first little plot twist, and it's a really important distinction to make. The arrangement of the electrons isn't always the same as the final shape of the molecule. I know, that sounds a little weird, so let's unpack it. So, we have two different things we need to keep track of here. On one hand, you've got the electron pair geometry. Think of this as the underlying scaffolding. It's the arrangement of all the electron regions, including bonds and any stray lone pairs. But on the other hand, you have the molecular structure. This is the shape you'd actually see. It describes the arrangement of only the atoms themselves, as if the lone pairs were invisible.
Now, the simplest case is when a molecule has no lone pairs hanging around. Take methane, CH4, for example. The carbon in the middle has 4 electron regions, and they're all bonds to hydrogen atoms, so its electron pair geometry is tetrahedral. And guess what? Its molecular structure is also tetrahedral. The scaffolding and the final building look exactly the same.
But things get way more interesting when lone pairs show up to the party. They're kind of like invisible bullies. You can't see them in the final shape, but man, they have a powerful influence on what that final shape is going to be. We call this the lone pair effect. And I'm not kidding about them being bullies. Lone pairs take up more space, and they push harder than the electrons that are tied up in a bond. So there's a pecking order. The strongest repulsion is between 2 lone pairs. Next is a lone pair pushing on a bond, and the weakest repulsion of all is just between 2 regular old bonding pairs. This little hierarchy is key. Let's look at the perfect example, water, H2O. The central oxygen atom has 4 groups of electrons around it. 2 are bonded to hydrogen, and 2 are lone pairs. So, since there are 4 groups in total, its parent electron geometry, that underlying scaffolding, is tetrahedral, just like we saw with methane. But, and this is the crucial part,
Those two big, bossy lone pairs are pushing down on the two bonds to hydrogen, squishing them closer together. And since the molecular structure only cares about where the atoms are, we don't see those lone pairs. What we see is the final result, a molecule that is bent. So check this out. You can actually predict the shape of pretty much any molecule with this simple 4-step process. First, draw the basic 2D Lewis structure. Second, count up all the electron regions around that central atom. Third, that number tells you the parent electron geometry. And finally, you just look at how many of those regions are lone pairs, and that reveals the molecule's true final structure.
Okay, this is cool. We can predict shape. But so what? Why does this matter so much? Well, here's the big payoff. A molecule's 3D shape is the ultimate decider of one of its most important properties, its polarity.
Think of molecular polarity like a game of tug-of-war. Inside a molecule, some atoms pull on electrons harder than others, creating these little directional pulls. But for the entire molecule to be polar, the overall shape has to be arranged in just the right way so that all those little tugs don't cancel each other out. You need a net winner of the tug-of-war.
And to see just how much geometry makes all the difference, there is no better example than comparing two of the most famous molecules around, carbon dioxide and water.
And this slide right here perfectly illustrates the entire concept. Look at carbon dioxide. It's a perfectly straight, linear molecule. The two oxygen atoms are pulling on the electrons, but they're pulling in exact opposite directions. It's a perfect tie in the tug-of-war, so the pulls cancel out, making the whole molecule nonpolar. But then you look at water. Because it's bent, the two poles on the electrons don't oppose each other. They combine, creating a net pull in one direction. That's what makes water polar.
So really it all boils down to two simple rules. For a molecule to be polar, first it has to contain polar bonds to begin with. You need a tug-of-war in the first place. And second, its overall shape has to be asymmetrical so that those poles don't cancel each other out.
And that's really the big takeaway here. A molecule's 3D shape is not just a piece of chemical trivia. It is the defining feature that dictates its entire personality, how it behaves, what it dissolves in, and how it interacts with the entire world. At this tiny level, structure is function.
And that leaves me with one last thought for you. Now that you know water is a polar, bent molecule, and the air we breathe, mostly nitrogen and oxygen, is made of nonpolar, linear molecules, what everyday things can you suddenly explain? Think about why oil and water don't mix, or how soap actually works. The answers are all hidden in their shape.